Hello, welcome to PhyzQuest. So this is the solution video for CSIR NET December 2019 Part B, question number 7. So the question is, the Hamiltonian of two interacting particles, one with spin 1 and the other with spin half, is given by H is equal to A S1 dot S2 plus B S1x plus S2x, where S1 and S2 denote the spin operators of the first and the second particle respectively, and A and B are positive constants. We need to find out the largest eigenvalue of this Hamiltonian. So 4 options are given and we need to choose the correct option. So let's get started. This question is based on quantum mechanics and the concept involved here is the eigenvalue problem. So here we are given a Hamiltonian of two interacting particles, which is H is equal to A S1 dot S2 plus B S1x plus S2x. So as you can see, it is a spin operator based Hamiltonian. Now when we talk about elementary particle, it's a purely quantum mechanical concept. Now these particles have their certain properties. Some of those properties we can correlate in classical mechanics, but there are certain properties which are purely quantum mechanical and have no counterpart in classical mechanics. Spin is one of those properties. Spin is an intrinsic form of angular momentum which is associated with the particle. Now the other physical quantities such as energy, charge, angular momentum, I'm talking about orbital angular momentum. Spin is also a quantized entity. That means it is expressed in terms of a quantum number and it has certain rules. Now both the magnitude and the direction of the intrinsic spin angular momentum is quantized. Now if the magnitude of the spin is s and it is represented in terms of the expression s square is equal to s into s plus 1 h cross square. Similarly, the direction of the intrinsic spin is also quantized and it is given in the form of Sz is equal to ms h cross. Here Sz is the z component of angular momentum. Here ms is the projection of the spin along the z-axis. Now this direction can be anything like x, y or z, but the expression will remain the same. Now if you consider a spin half particle, here the magnitude will be, that is s, will be equal to half, but the ms value, the projection will be plus half or minus half, where plus half is corresponds to the upspin and minus half correspond to the downspin. In quantum mechanics, in terms of the eigenvalue equation, the representation will be, now if s square and sz are the spin operator, if you consider them, then the eigenvector can be written as in terms of the bracket terminology, that is s ms. So if this is the eigenvector and when it is operated with the operator s square, it will be s when operated with the bracket sms, it will give s into s plus 1 h cross square sms. So as you can see, it's an eigenvalue equation. Similarly, when it is operated with sz, it will give ms h cross sms. So here eigenvalue is ms h cross. Now in this case, in the question, we are having two interacting particles. So one of them has spin 1 and the other has spin half. So here they have their corresponding ms value. So the ms value for the first particle will be minus 1, 0, plus 1. So now if we want to write in terms of the terminology of the eigenstate, for the first particle it will be 1, 1, 1, 0, 1, minus 1. Here s, the value of s is 1, which remains the same, only the ms value is changing. So this is the eigenstate representation for the first particle. Similarly, for the second particle, ms is equal to plus half and minus half. In similar fashion, the eigenstate for the second particle will be half half and half minus half. Now in the question it is given that the two particles are interacting. So that means here we have to calculate the total spin as well. So the total spin will be S is equal to S1 plus S2. Now here S is the spin is I'm talking about is a vector. So vector S will be equal to vector S1 plus vector S2. But the magnitude, if you consider, magnitude S will be equal to modulus of S1 plus S2 to modulus of S1 minus S2. Because when you make the total, the particle may have, the direction of the spin may vary. That is why S1 plus S2 to S1 minus S2. Now here if you put the value, it will be 1 plus half, that is 3 by 2, to 1 minus half, 1 by 2. Here 3 by 2 is the maximum value and 1 by 2 is the minimum value. Now for the value of magnitude of S, for both the value, if you want to write the ms values, possible ms values, it will be for the first, that is for 3 by 2, it will be minus 3 by 2, minus half, 1 by 2, 3 by 2. So here for the states will be minus 3 by 2 minus 3 by 2 minus 3 by 2, 3 by 2 minus half, 3 by 2 half, 3 by 2, 3 by 2. So these are the possible eigenstates. Similarly for the minimum value half, the ms value will be half minus half. Here the eigenstates will be half half and half minus half. So here the reason for writing down all the possible eigenstate is to choose those eigenstates which will give you the largest eigenvalue. Because in the question we are asked to, we are given a Hamiltonian which is based on spin operator, and we need to calculate the largest eigenvalue of the Hamiltonian. So here the largest or the highest eigenvalue will be decided by those eigenstates whose ms value is highest, because s value will be the same but the ms value will vary. So here we need to choose those eigenstates whose the ms value is highest. That means for S1 we have to choose the highest eigenstate, for S2 we have to choose the highest eigenstate, and for total spin also we have to choose the highest eigenstate. Similarly, so here in that fashion the those eigenstates will be, for S1 it is 1 1, for S2 it is half half, and for the total spin it is 3 by 2 3 by 2. So next is to proceed with the calculation of the eigenvalue. So here now the given Hamiltonian is H is equal to A S1 dot S2 plus B S1x plus S2x, and the eigenstates we have got is this for S, S1 and S2. Now this Hamiltonian, here if we omit the bracket, we can rewrite this Hamiltonian as A S1 dot S2 plus B S1x plus B S2x. Now when the spin eigenstate operate on this Hamiltonian, we can, that is the state bracket SMS, if we operate when operated by this Hamiltonian, the equation will be like H SMS will be equal to A S1 dot S2 SMS plus B S1x SMS plus C plus B S2x SMS. So here the thing is there are three terms. So we'll solve them one by one. First, let's go ahead with the A S1 dot S2 operating on the state SMS. So here we have discussed about the spin operator S square and SZ. There is nothing mentioned about S1 dot S2. So how to do this this eigenvalue, solve this eigenvalue equation? So here we have to actually consider the total spin. So here total spin, as I mentioned, vector S is equal to vector S1 plus vector S2. So if we use that equation, that is S dot S, that is S square, this will be equal to S1 square plus S2 square plus 2 S1 dot S2. Here we have S1 dot S2 term as well as S2 dot S1 term. Both are equal, so it will be ultimately 2 S1 dot S2. So from this we can write the expression for s1 dot s2, which is equal to s square minus s1 square minus s2 square divided by 2. So here instead of s1 dot s2 we will use this expression. Okay, so let's do that. So here we already have a constant a here, and there is a half in this expression, so it will be equal to a by 2, that is s square operating on SMS minus s1 square operating on SMS and minus s2 square operating on SMS. So the thing is, here I have written a general expression, that is I have not given any values here for the spin and the projection. So here our purpose is to find out the highest eigenvalue. So in place of the eigenstate we have to write down the highest eigenstate. The eigenstate giving the highest eigenvalue. Okay, so for s it will be is 3 by 2 3 by 2, so we will rewrite this as a by 2. This will be s square 3 by 2 3 by 2 minus s1 square 1 1 minus s2 square half half. So this is for s, that is the total spin, the highest eigenstate is this. For s1 it is 1 1, for s2 it is half half, so we have put there. Now next is to solve. Now we can easily operate on this state. So as I mentioned, we have to use the formula s square SMS is equal to s into s plus 1 h cross square SMS. Okay, so now here in the first term, this expression we will write as a by 2. The first term here s is 3 by 2, so this will be 3 by 2 into 3 by 2 plus 1 h cross square. Second one is minus 1 into 1 plus 1 h cross square, and the last one is half, that is s is half, so minus half into half plus 1 h cross square. So when you solve it, it will be, now here you can take h cross square common. So if you take h cross square common, this will be equal to a h cross square by 2, and here this will be 3 by 2 into 5 by 2 minus 2 minus half into 3 by 2. So this, when you again solve it will be a h cross square by 2, it will be 15 by 4 minus 2 minus 3 by 4. So here 15 by 4 minus 3 by 4 is 12 by 4, which is equal to 3. So 3 minus 2 is equal to 1. So ultimately this answer is a h cross square by 2. So the first term gives the eigenvalue a h cross square by 2. Next we will proceed with the rest of the two terms. First is b s1x. So when b s1x is operated with these states, so what will give, let's see. So b s1x when operated with SMS, it will be equal to b s1x 1 1. Why? Because that is for first, the s1x corresponds to the first particle, and for the first particle the highest eigenstate is this, so we have put that. Now in order to solve this, we have to use the same expression, that is sz SMS is ms h cross SMS. So this is, though I've already mentioned that here direction is not important, actually it is same for any of the direction. So for x also we can use the same expression. So ultimately the result will be b into 1 into h cross, because ms is 1 here. So this will be equal to b h cross. Now the last term is b s2x. So here when b s2x is operated with SMS, it will be operated for the highest eigenstate, here it will be half half. So b s2x half half, same using the same formula for sz, here the result will be b into half into h cross. Here ms is half, so this will be equal to b h cross by 2. So we have got all the expression for the three terminologies. Next is to write down the total of the three expression, because the Hamiltonian consists of these three expressions. So the eigenvalue will be, when Hamiltonian operated on this state, this will be equal to a h cross square by 2 plus b h cross by 2. So this will be equal to a h cross square by 2 plus 3bh cross by 2. So if you take half common, it will be half into a h cross square by 2 plus 3bh cross. So this is our answer we have calculated. This is the highest eigenvalue. Next, look at the options. So here, if you look at the option A is matching with our calculation. So the correct answer for this question is option A.